Yeah, I've got both open right now.
Okay, so you're going to be live now.
Awesome.
All right, go.
Cool. Well, hey everybody, welcome to another episode of Deep Random Talks. I think this is episode 17, so time really flies. I think we started this back in February. So yay. Today we've got Alex joining us, and Amir is hiding in the shadows because he doesn't have good internet, unfortunately, but that's okay. So yeah, Alex, can you introduce yourself?
Yes, my name is Alex Asamosini. I work as a staff data scientist at Shopify. Yeah, I'm drinking tea, so that's my drink of choice today.
Nice.
Yeah.
Yeah, for me, I have like a smoothie that I haven't finished yet from breakfast, and then I also have some water. I don't know if anybody recognizes the logo of this, like on this water bottle. It's a defunct ride sharing company, I think. Or like, anyways, yeah, got it for free. I can't remember what brand it's from. The brand does not exist anymore because they failed. Okay, so yeah, usually Amir asks me what is new. Not much is new with me. I'm still working on this app, Food Shake, so it lets you translate recipes from non-vegan to vegan. I'm currently thinking about like maybe I need to present this as non-plant-based to plant-based because I think vegan is a bit of a scary term. But anyways, if there's anybody who's watching who's interested in exploring plant-based eating, please message me. I'd love to chat with you. Anyways, okay. So today we're talking about optimization, right, Alex?
Yes, we are.
Okay, cool. Yeah, so there was an interesting paper that you shared by DeepMind that came out in September 2020. So kind of old now at this point. It focused on traffic navigation and was a collaboration between DeepMind and Google Maps. So the quick overview is that DeepMind and Google Maps partnered, and then they were able to improve real-time ETA, so estimated time of arrival, on Google Maps by up to like 50% in, I think, Berlin, Jakarta, Tokyo, Washington, D.C., all of this. And how Google Maps currently works is they analyze live traffic. I think they use cell phone signals or cell phone data, and they get a real-time snapshot of traffic. And then based on that real-time snapshot and then other factors, they're able to predict future traffic. So like in the next like hour or so, what is the traffic going to look like? And then that helps predict the ETA. And they ended up doing some work with graph neural networks. And again, to get a bit deeper, but still high level, they had like a two-step model, I think, where they define super segments on roads. So that would be like a Toronto specific example would be Ossington and Bloor. They're two roads that cross. They're like orthogonal. Those are two different super segments. And then they have a second model that is a graph neural network that predicts like traffic flow and traffic volume across those super segments. And then from there, they combine the two and then predict ETA. And they use some optimization method that, Alex, you were telling me is pretty complex called metagradients. I'm not sure if they sort of have this optimization method applied to both models, if it's just to one model. But yeah, what's up with this? What's up with this optimization method? Is this like the secret to this DeepMind paper?
It might not be the whole secret, but yeah, metagradients is what it's called. It's a pretty interesting optimization method because as we're going to talk, optimization methods are kind of defined by their update rules. In this case, their network that they were optimizing, the neural net that they were optimizing, was so complex that they created a network, almost sort of a networkception. They created a network, a reinforcement learning network, to learn update rules using the gradients that they were calculating. So basically, they had a second neural network that was giving them ways or rules or ways of updating the network. And they called that metagradients, gradients about gradients. So you feed the gradients. And we're going to talk about what gradients are. I think a lot of the viewers might actually know, but we're going to talk about gradients in some detail. But they have this second network that basically decides for them what works best in terms of optimizing their primary networks, as you mentioned, that have the super segments, but also once you've decided on what the super segments are going to be, what part of a highway, what part of a road are you going to segments, then you're going to decide what is going to be the best connectivity structure and the cost structure on that to estimate the ETAs, and then to route people from A to B, and then to basically sort the routes based on the ETA that people can get. So yeah, the meta gradients are a pretty complex and complicated optimization algorithm. They kind of are self-referential in the sense that you're using another neural net to optimize a primary neural net. But what we're going to talk about today is going to be pretty simple in comparison.
But I know you're very passionate, I would say, Alex, about optimization. And I'm thinking you probably would ace any machine learning interview you have where they ask you about different optimization methods.
I don't know about that, but I'm like, the traffic case is something that's really interesting to me, in the sense that one of the first instances that I came up with optimization as a concept was really the traffic. You know, if you have a straight segment of the road and there's a few traffic lights, it's not always the case that if you basically drive the speed limit, drive the maximum speed that you can, that doesn't really minimize your ETA. Sometimes you have to adjust yourself with the lights in order to get there faster. So this was a use case that I first came across that was first like gave me the intuition that, okay, optimization is something that is worth to think about. It's something that it might be worth studying from a mathematical point of view. It's not just normal intuition from daily life. And I ended up doing some stuff about it in grad school. But you know, it kind of like tied into network optimization, tied into not exactly road networks, computer networks, but then basically this paper is very close to my heart because of that, because it actually talks about how do we take this optimization ideas and apply them to another optimization that people have been doing for ages, pretty much. For ages, people have been trying to use computers to optimize how to travel on the roads, how to travel during the rush hours, like in the cities, in mega cities and other places. And they've shown an improvement in real life performance.
Yeah, that's very cool. I love that you first thought about optimization with regards to traffic and driving. Were you old enough at the time to know that what you were talking about was optimization, or you sort of like weren't quite able to verbalize it, and then once you got to grad school, you realized, optimization is what I've been thinking about all this time?
Not necessarily. I don't think I was old enough to actually be able to verbalize or know enough
Yeah.
math to conceptualize that this was something. But then I was like, okay, this is something to be at least symbolically thought about. This is not something that you just kind of like memorize, okay, or like drive the speed limit and you're going to be there fastest. Just
Yeah.
clued me in to the complexity, but not necessarily in the sense of giving me the, I'm guessing, the mathematical basis to think about, okay, uh, what is an optimization problem? What is a cost objective function? What is a gradient? What is gradient descent? A lot of these things that we're going to talk about today.
Yeah, and I guess maybe backing up a bit, like what really is optimization? Because as thinking about when I was young and before I had learned any math really, I would think of, well, I probably wouldn't even know what optimization was, but let's say like a bit further in life, optimization, I would think of it as like making the best of a situation. That's optimization, like trying to drive as fast as I can given the constraints of the traffic lights, which will stop me. And I want to get to my destination as fast as possible. That's like one definition of optimization. Then there's the kind of math optimization definition, which is more like you're selecting the best parameter out of a set of possible values. What would your definition of optimization be? I guess, like mathematically speaking.
The mathematical definition, to your point, is very close to the, I mean, very close to a natural language description. It's not that far off. You have a set of parameters. You have a cost and objective function. So you try to make the best in life, but you try to make the best of a certain mathematical problem. You have a certain function of a certain set of parameters. Now, this function does not necessarily measure your utility in life in way someone, in economics might actually do it, but it doesn't necessarily measure that, but it measures something, some problem that you have some interest in. It might be driving from A to B. It might be your odds of winning the lottery. It might be your machine learning model with millions of parameters that you have to set up in a way that it classifies as images of cats and dogs properly. So you have a function of parameters and you want to set those parameters, and you have a bunch of constraints. Those parameters can't change arbitrarily. To your point, you can't really hack OLG, for example, if you want to kind of increase your odds of winning the lottery. So constraints have to be put into the problem description as well. But the general gist of the problem is that you have a function of a set of parameters, and this function represents some objective cost that you want to minimize. And then you make a series of small moves, small incremental calculated moves. And then you basically optimize the function. And optimization starts, I think, for a lot of us with gradient descent. What is gradient descent? In this case, if we have this function of parameters, which might be our neural network with a lot of training examples, we want to kind of minimize the loss that we are seeing from our training examples onto the preferred truth labels. We take of steepest descent in that surface, in that objective loss function, and then we go in that direction. It really works, but it also doesn't for a lot of neural nets, because what we call gradient descent is really a full batch gradient descent. So we take the gradient of the cost function with respect to the entire set of training examples. In deep learning, in a lot of cases, we don't have enough memory to store the entire set of training examples in our computer RAM. So we go with stochastic gradient descent, for example, which is where we take a mini batch instead of computing the gradient over the entire set of images that we have to classify. We take 100 of them at a time, 1,000 of them at a time, and then calculate basically a statistical approximation to the gradient, and then take a step along that gradient. And this step is proportional to something like a learning rate.
So just to check my understanding of it, so it seems like, yeah, like I love everything that you're getting into, and this is reminding me of many different things that I need to brush up on. So first of all, gradient descent seems to be, yeah, this like sort of first step into optimization for machine learning. So can you give a just quick overview again, like what is gradient descent? Why do we care about it? Also touching on maybe why it matters for problems to be convex.
Yeah, so gradient descent is basically taking the direction of the gradient of a function. And what is the gradient of a function? Gradient of a function is a direction, it's a vector in the space of parameters that basically points locally to that function, increasing the maximal value by the maximal value. So it's a direction of steepest change, local basin of the function. And that's the reason we call it gradient descent. We take the gradient, which is a mathematical tool we can kind of calculate based on the shape of the function, based on the parameters of the function, and then we move in the direction of the gradient. Now, the importance of convexity here is that if that basin is not convex, if the function is not convex, gradient descent is not guaranteed to converge to any sort of minimum. Whereas if we have the guarantee of convexity, we can show that gradient descent slowly but surely converges to a minimum point of the function over time.
And so in sort of the most simple example, like you have your like loss landscape, and maybe it'll look like a U or something, and you're like
Yeah,
traveling down that lost landscape, and eventually you're hoping to get into this little valley, and this represents like the best parameters for your network, for that function that your network represents. But it's not always like that, right? So is this
exactly.
where we then move to like, I guess I'm wondering, when we move to stochastic gradient descent, like what requires us to move from just gradient descent to stochastic gradient descent?
Stochastic gradient descent helps with that, but it's not the, there is really no alternative. Like convexity in some sense is needed for any sort of guarantee on global optimization. If we want to get global optimums, we need to have convexity, because otherwise we might have a lot of local minima. And all of these methods, gradient descent and all the enhancements and improvements, are local methods. They only look at the local section of the function. So if you don't have guarantees of convexity, we don't ever have guarantees of convergence to the global minima, but we can have guarantees of convergence to local minima. Now, one of the things that we have for a lot of deep neural nets is that local minima are good enough. They generalize well, they learn the problem. So we local minima in some sense. A lot of these DPUs that are kind of stacked together in the lost landscape. And it doesn't really matter which one of those we converge into. So that's the thing with stochastic gradient descent. Stochastic gradient descent, a lot of the times, to your point, doesn't necessarily take us to the global optimum, doesn't get us away from the need for convexity, but makes it less of a problem, makes it much less of a practical problem. And really in optimization, one of the themes is that practice really trumps theory. We have a lot of theory. We have to really kind of temper that with what we've learned from practice. So to your point, actually, yeah, exactly. These methods help with a lot of that non-convexity as well.
Yeah, I think it's really interesting what you're saying about practice versus theory, because I know that different optimization methods. We've already talked about 3, I guess. There's that meta gradient method that the DeepMind traffic navigation paper uses. There's also gradient descent. Then there's stochastic gradient descent. And then I know that there's different methods like ADAM, RMS prop, I think AdaGrade, and then there's many different things, or like methods that change small parameters in the like optimization, I guess, equation. So if we were to continue to build from like simplest, like first principles upwards, we have gradient descent, stochastic gradient descent, and then what would come next and in what circumstance, I guess, theoretically and also practically speaking, would we want to use that other method?
So the next set of methods that come up from stochastic gradient descent are momentum methods. So imagine we are trying to do a 2-dimensional ravine, or a river valley, and that is our lost landscape. So it's very narrow along the direction of the walls of the valley, and it's very deep along the base of the valley. The problem with learning rates, steps that we are taking on gradient descent and stochastic gradient descent, is that they can be too high in one direction and too low in one direction. So we might be bouncing up and down the walls of the valley and making too slow of changes along the base of the valley, which is where we have to actually make changes to get to the minimum of the loss function.
Yeah, and just to jump in, so the learning rate is like the step size, right? So if you're traversing down your landscape, if you have a larger learning rate, you like make a bigger jump. If it's a smaller learning rate, you're kind of slowly traversing downwards into the like local minima.
Exactly, and you're absolutely correct. And learning rates are part and parcel of optimization in a sense in neural nets. It's really important how we, when we are starting training a neural network, our learning rates and our step sizes have to be bigger because the neural nets are still very much uninitialized. So we have to kind of take bigger steps in order to get closer to the vicinity of a minimum. And then as we train our networks, our learning rates have to be tempered. They have to be made less in order to make sure that we are not overshooting the actual. So the act of tuning the learning rate itself is very important to how the networks operate, to how the optimization of the network parameters operates. And it often happens that our functions are kind of like that. They're kind of like those ravines, deep valleys. We don't have a learning rate that works well in all directions. So one of the methods that we have come up with is momentum methods. Momentum methods basically are like adding momentum, adding mass to a ball that's kind of rolling down the valley. So if a direction consistently is giving you improvements in your parameter values, you add to your updates to your step sizes in that direction. If a direction is consistently bouncing back and forth, you penalize that direction in order to make sure that you're not really taking steps that are not rational in the pursuit of optimizing your cost function, your loss landscape.
And maybe this is getting into the weeds a little bit, but that update parameter that, like, I guess, exploits good directions and I guess penalizes directions and updates that are not as beneficial to the network. Is that a learnable parameter, or is this like getting into different kinds of methods?
Oftentimes it could be a learnable parameter, but people generally put it to something like 0.99 or 0.9. So it's pretty close to 1. So it's a high momentum. Like we accumulate gradients pretty much. We try to take a look at a global picture, because you remember I mentioned gradient descent is a local method. Momentum adds a bit of history. Momentum gives us something to look back, like it's a window of look back into how the function has behaved over the past few iterations and the past few iterates. So generally speaking, it's a learnable parameter. Could be a learnable parameter, but people generally don't touch it, they probably go with 0.99,
Mhm.
where the value is sometimes people go with 0.9. Then again, it's very much fixed and set in stone for a lot of methods
Right.
that we are talking.
Yeah, like in practice, those values work. Yeah, that makes sense.
Yeah.
So yeah, I guess to recap so far, we've talked about gradient descent, like basic gradient descent, I'm going to say. So gradient descent, stochastic gradient descent. Now we're talking about momentum methods. So what are the different kinds of momentum methods? Because I know there are a few. Atom, I think, is a momentum method, is RMS prop, and then AttaGrade, I think that's something else. Yeah, do you mind going over
Yeah.
that and helping me out?
Yeah, sure. So one of the other problems that we have with deep neural architectures in particular is that a lot of the parameters are sparse. If you think of a layered neural network, as we start training the network, we are learning features in the initial layers. As the training progresses, the initial layers almost start to freeze and almost start to into their final value. So the updates coming their way would be sparse. But also, as we talked about it before, we have to temper our learning rate as well. As we are progressing through learning, less and less bigger step sizes are needed to be applied. So we have to kind of temper that. We have to scale the gradients in some sense because we don't want the network to forget so much of the things that it has initially learned because of our optimization methods. So the difference between all of these methods is kind of how they do the scaling of the gradients. RMS prop and AttaGrad are pretty much similar. They are not momentum methods per se, but they do a gradient scaling. They kind of scale the gradients. They try to, for parameters that are very sparse, they try to make the updates bigger. For parameters that are very frequently updated, they try to make the updates smaller so that there's some semblance of balance, some semblance of proper learning rate for each parameter maintained. Atom is pretty much the basically the entire set of these methods on steroids. It's kind of like we mix a momentum term, but we also have a gradient scaling term. So we both take care of momentum, how to basically track directions that are consistently giving us good optimization values, good improvements in the score, in the loss score of the loss landscape of the function that we are trying to optimize. But also it has gradient scaling built in as well. So as we move towards the end of optimization, if our initial layers, for example, don't need to be updated as often, it makes sure that whenever an update comes for them, which has to have been something significant, has to have been maybe we learned a feature wrong in the initial layers, we need to kind of correct for that. Atom basically has both of those things. It has gradient scaling and it has momentum. As ARM and AttaGrad don't have those things necessarily.
Yeah, it's really interesting hearing you explain all of this because I'm thinking like it's a lot of people, and this is a generalization, probably get introduced to neural networks and jump straight to complex methods such as Atom, but really there's a lot of math that goes into actually understanding what Atom does. And when you actually implement it in Python, for example, you can just set like optimizer equals Atom and that's it. And you sort of don't have to think about it that much. But how like difficult is it to actually implement these different methods in practice? I think most of them are available off the shelf, right?
Most of them are completely available off the shelf, and there are pretty optimized implementations. I think if you go through the recipe, we have resources as well that we have linked to that even discuss the mathematics behind them. So if someone wants to do learning by doing, they can learn by doing themselves. But for the most part, you can use Atom these days if you don't care about the quality, let's put it this way, if you don't care about the quality of the minima, and it works for a surprising variety of classes of neural network architectures, it's a pretty good option. You can use it. You can use it off the shelf. And if you really don't care about the time of training, you can use stochastic gradient descent. Stochastic gradient descent is still the gold standard in terms of there's the most amount of theoretical guarantees about how it performs and how it behaves. But then again, it's very slow. It's very zigzaggy. It's approaching those minima of the loss landscape of the function.
Is it expensive to use as well? Because I'm just thinking of like various research papers that I've read. I think Atom seems to be the most common method used. maybe because of speed, like you want to get your research done quickly?
Yeah, so with Atom, you don't have to run as many epochs of training, as many uh, even like like it gets you there. It gets you there fast, and the quality is often pretty good. It's not the exact minimum loss if you are very careful with like a lot of checkpoints, a lot of warm restarts, SGD with a lot of learning rate schedules. And if you were extremely careful with SGD, you can get probably after like 50 trials and errors, you can get something better than what Atom produced. But oftentimes
Mhm.
Atom gets you there in 1/50th of the time, and less, to your point, much less of a headache. So for people that want to kind of publish papers about neural nets and new architectures and learnings and tasks, it's a much better choice. But for people that want to kind of explore optimization or pushing the limits of optimization, kind of like that DeepMind paper that we were talking about in the beginning, it does make sense if optimization can become a bottleneck in your architecture. It does make sense to go into the into the flow of things, see how things work under covers. Like like there's a lot of things that have been written about Atom, how even like Atom itself is wrong. There's a lot of enhancements you can make to it and things that are incrementally improving on it. But seems like it's hitting a sweet spot in terms of being a pretty good general purpose optimizer for the neural net architectures that we have. Deep architectures with residual connections and batch norm, and it's just a good match for them.
Mhm. Yeah, so for industry practitioners like ourselves, so Shopify, also you were at Loblaw Digital before, and maybe for people at say Pinterest and Meta who have very machine learning heavy products, um, what sort of optimization method do you think would make sense? Like, is it worth spending time into finding like the optimal optimization method, or would SGD often work, like assuming that the development process is fairly slow if there are like a lot of stakeholders?
I think SGD might work as, yeah, like they work. They like for practitioners in ML. A lot of the times, to your point, optimization is not something that comes to the fore. It's
Mm-hmm.
not a make or break thing, but it is worth noting that it's one of the pillars that we are building upon, and a lot of these things interact with one another. A lot of the choices of architecture that we can make, especially when you come to more complicated architectures like reinforcement learning or physics-based neural net architectures, things that are inspired from physics, things that are inspired from laws of nature. It might actually be worth thinking about how the optimizer interacts, how we initialize the weights, how we optimize the optimizer itself, how the learning rates are cycled. Are we using snapshots? Are we using warm restarts? Even things like Bayesian optimization for versus like grid search. Uh, but there's a scale where that becomes more important. But for the most part, to the point that you mentioned, for industry practitioners, uh, Atom is pretty good. Even SGD these days, you know, video cards and TPUs are pretty good, so you don't have to really worry about that much. We are in pretty good shape when
Mm-hmm.
it comes to optimizing architectures, unless you're pushing the boundaries of research, in which case you have to really think about how all of those things interact.
Yeah, definitely. So to be a bit contrarian, then I'm wondering if we can simply use SGD as an industry practitioner, why even care about all these different optimization methods? Of course, if you're applying for some ML engineer role, I think oftentimes that you might get, as part of the interview, quizzed on different kinds of optimization methods. So kind of feels like it's a textbook thing you need to know. But in terms of like practice, is it possible that we don't actually need to know about any of this?
I think that would be the ideal kind of end state. At some point, maybe you can be completely on an ML engineer curriculum and don't know anything. It's completely black box. You say optimizer, optimize. There's no SGD, there's no Atom, there's no anything, any notion of the optimizer. But I don't think we're there yet. I think there's still value in having played with these things, maybe not on a theoretical level, but on a practical level, and having known them to some extent. But I think that's the ideal that a lot of people are straight towards to kind of achieve in the next few years, maybe, or the next little while. Who knows?
Yeah, it's
Yeah,
really interesting because it makes me think like the specific skill set to do machine learning will change over time. It sort of becomes more computer and or not computer, software engineering and computer science rather than math, let's say.
I think so as well. It's becoming more SWE centric as opposed to
Hmm.
math centric. So that is definitely a trend that I've noticed.
Yeah. How do you feel about that? This is the random part of the conversation.
I don't feel I don't feel that's a bad thing necessarily. It makes everything more accessible to a wider audience of people. So that is a good thing. Um, I feel like there's so much incremental value to be derived from still doing academic research and doing frontier of science research that people with math skills are gonna find themselves pretty easily employed. So that's not a concern either. So yeah, I'm not really concerned with that. How about you?
Yeah, I think same as you. It is what it is, and anything we can do to sort of democratize these tools and make it more accessible for people who don't necessarily come from one very specific background, I think that's great. I think a few years ago I would have been a bit more terrified of that idea, like, no, my math degrees are not going to good use now. But I mean, really, that's not the case. And at the end of the day, we want to solve business problems and provide business value and all that fun stuff. So yeah, if the tools are easier to use for more people, I think that's great. And in terms of the math a bit more, so you had mentioned that there are different ways to um, adjust atom, and so again, like recapping more so for myself. So there's or gradient descent, stochastic gradient descent. There's then momentum methods, and then there's methods that adjust the gradients as you kind of move through your optimization problem. Is there any other category that we haven't touched on yet?
In optimization theory, from a very mathematical point of view, there's a broad category of second order methods like Newton methods. But because for deep neural nets, we often have very large problem sizes in hundreds of millions and billions of parameters. We don't really use second order methods and second order problems, second order theory as much for neural network optimization. It's a very interesting mathematical problems to look at. It's uh, to my great sadness that it's not used more in neural network optimization, but that's what it is. I feel like some of the gradient scaling work, some of the work on even enhancements to Atom and other methods, they do discuss how many of these random tweaks that people make to equations in papers, like things that seem to work in practice, they do have some uh, theoretical interpretations when you interpret them in the framework of second order methods, and they're like approximations to Newton's method in some limit of the parameters. So it's pretty interesting from that point of view if you're that kind of person that is interested in mathematics of optimization to kind of go and read those papers and see how a lot of these things, maybe 3-4 years after they're discovered by practitioners, theoreticians come to kind of clarify the choices made, and they are often very interesting insights that we can gain from reading those publications and from getting those insights. Uh, but yeah, that's the other big class of optimization methods, the second order methods, which involve like inverting huge matrices that are basically a no-go when you're working with the size of problems
Yeah.
that you're working with deep neural nets these days.
Yeah. So those papers you mentioned, are those in the recipe that we'll be sharing later? Oh, Alex, you're muted.
Some of those papers are in the recipe. I try to be, with the resources that I shared, I try to be more uh, including and involving resources that were more broad-based and a more broad review of the used, but I can add a bunch of those to the recipe as well. I can add a bunch of those that are specifically about how gradient scaling methods are kind of recasting of second order methods, but in a way that's computationally efficient for the way that we have to optimize our deep neural nets. But there's a very interesting video from DeepMind XUCL that goes through some of that in some detail. So I definitely recommend anyone to watch that video if they're interested in knowing how some of these things actually connect. Some of the theoretical parts of mathematical optimization connect with some of the more practical things that practitioners do.
Yeah, I'm definitely going to check out that video. I find it interesting because in my math undergrad, which was more so like a survey of different mathematical areas, I studied second order methods, but never came across gradient descent, atom, RMS prop, anything like that. I think because I wasn't in the computer science department. So I find it interesting how, at least where I went to school at McGill, there's like this divide between the kind of like mathematical methods and the more computer science focused methods or computer science applications, um, rather than like surveying all of these methods broadly. Not sure if that's been your experience. I'm sure in grad school, if I was to study like more optimization, then I would have come across all these methods at once, but I only started learning about gradient descent once I became interested in machine learning.
Interesting you say that. That's been my experience as well. There's a huge divide in what people do as practitioners in computer science and what people do in math departments and optimization. You know,
Mm-hmm.
example that I went to, there's the combinatorics and optimization. A lot of people are all about combinatorial optimization, which is pretty interesting as an area. And there's a lot of work on continuous optimization, but all of it is second order methods, you know, conjugate gradients and quasi-Newton methods. Not a lot of work on online optimization or like machine learning centric methods or theoretical, at least theoretical foundations for those. But seems like because of the popularity of deep learning, more and more of theoreticians are trying to kind of get into the weeds of trying to figure out what is it that is working about these methods, and maybe using toy models or using some toy functions, basically getting to the point of solving the problem of why do these things actually work so well.
Yeah, it makes sense. I mean, if you're driven by publications, then why not like broaden the scope and focus on, yeah, more computer science ML use cases. So I'm wondering, Alex, I guess I would just ask, like, given all of this, now what? I'm thinking about machine learning that I'm going to be doing in my work at Shopify. Um, I probably will use whatever the in-house ML system suggests to me in terms of my optimization method. I'm wondering, like, we actually both happen to be at Shopify. Do you have an idea of like your favorite optimization method? Do you think you'll just use what's suggested to you by the platform? I'm curious about from your perspective what you would do.
I think my favorite is Atom, and I've mentioned kind of in passing why, but to your point, it's at a point where whatever the platform suggests is probably something and works. So I wouldn't really disagree with that. That's 100% agreement from me on that as well.
Yeah, cool. Glad we are aligned. Yeah, and are there any call to actions you want to share with the audience? From my end, my call to action would be if you're mathematically inclined, I would say check out that UCL DeepMind video that Alex mentioned. It's going to be in the recipe that we will share probably tomorrow. I think that is going to be a very interesting video to watch. I'm curious to see how parallels can be drawn between, yeah, like gradient descent and methods that I'm more familiar with from undergrad, like Newton's method and other second order methods. But yeah, what about you, Alex? Any call to actions?
For me, another resource in the recipe that I suggest that anyone that wants to go deep kind of definitely read up is there's a write-up by Stephen Luder in the resources section that covers a lot of the first order methods in very great detail. There's derivations of all the equations that you would like to see. And yeah, I definitely would recommend that if people want to kind of go more deep into first order method.
Awesome. That's great. So there's no questions from the audience, but you can reach all of us on Slack, the ACE Slack. You can reach us on LinkedIn, check out the recipe, and you can even feel free to create your own recipes on the AI.science aggregate intellect website. I think maybe Amir will be happy for me giving this little plug. They have a nice Chrome extension that's really easy to use. So you can, yeah, create your own recipes, continue your learning, and share that with your friends. So yeah, thanks, Alex.
Thanks for having me.
Okay, have a great day, everybody.